Signals and Systems, DT Fourier Transforms, Part 1, Series on Signals and Systems, Lecture number 5.11. DTFTs stand for Discrete Time Fourier Transforms. Like other transforms, these are also used to convert a time domain signal into its frequency domain. These are similar to CTFTs, which stand for continuous time Fourier transforms. However, there is a major difference between these two. DTFTs are limited to discrete time domain, whereas CTFTs are confined to continuous time domain. Both transforms, however, are relevant when the signal or sequence is non-periodic. In the present session, the focus is on definition of DTFT, its properties, and DTFTs of certain standard sequences, and also its relation to DFT, discrete Fourier transform. All these aspects and some more are also considered, discussed, described in the present session. Now, let us move to begin the session. A few points regarding the importance or significance of DTFT are considered under definition. In signal processing, the DTFT is a form of Fourier analysis that is applicable to a sequence of values or samples of a continuous time signal. Sequence is usually derived by sampling a continuous time signal. DTFT is a kind of Fourier analysis that is applied to our sequence. The term discrete time refers to the fact that the transform operates on discrete data. DTFT is relevant or applicable only on sequences, discrete data. In these sequences, the interval usually has the units of time. From uniform samples, it generates a function of frequency that is a periodic summation of the CTFT of the original continuous function from uniform samples from the sequences, which are uniform samples. DTFT generates a function of frequency that is a periodic summation of CTFT of original continuous function. In these 3 points, notice the basic theme underlying is connection between DTFT and CTFT, connection between discrete time domain and continuous time domain through the application of Fourier transform. Now, let us move to consider the definition. The DTFT pair of a sequence of length n capital N and angular frequency omega. Omega is 2 pi by n. It is defined as DTFT pair. Pair indicates time domain signal and frequency domain signal or sequence. The discrete time Fourier transform of a sequence x of n. DTFT, it is indicated by capital X of omega. By definition, it is equal to sigma n equal to minus infinity to plus infinity x of n e power minus j omega n. This is forward transform or DTFT of the sequence x of n. Inverse transform. It gives x of n from x of omega. X of n sequence is equal to 1 by 2 pi integration over 2 pi x of omega e power j omega n d omega. Notice the DTFT itself is a continuous function of frequency. X of n is discrete time signal, but x of omega is continuous frequency signal. Now we consider properties, important properties of DTFT, discrete time Fourier transform. Linearity. In simplest possible terms, linearity means superposition principle. If a system or a transform obeys superposition principle, then we say it exhibits linearity. Mathematically, it is stated here as DTFT of A x of n plus b y of n is A x of omega plus b y of omega. Here x of omega is DTFT of x of n, y of omega is DTFT of y of n. A is multiplying x of n in time domain, b is multiplying y of n in time domain. These two are constants. Same constants are multiplying x of omega, y of omega in frequency domain. So, in word form, one can state that DTFT of weighted sum of two sequences is same weighted sum of the DTFTs of individual sequences. Now we move to another property, time reversal. DTFT of x of minus n. X of minus n is a sequence. It is equal to x of minus omega. Time shifting. DTFT of x of n minus n naught. It is equal to e power minus j omega n naught x of omega. Another property, frequency shifting, x of n e power j omega naught n. Its DTFT becomes x of omega minus omega naught. Time expansion, DTFT of xm of n is equal to x of m omega. Modulation property, DTFT of the product x of n cos omega naught n, product of two sequences. It is equal to half x of omega plus omega naught plus x of omega minus omega naught. Another property, conjugation. DTFT of x of n conjugate, it is equal to x of minus omega conjugate. Some more properties of discrete time Fourier transforms, DTFTs. Frequency differentiation. DTFT of minus j n x of n is dx of d omega. Notice multiplication in time domain. It is appearing as differentiation in frequency domain. First difference property. DTFT of x of n minus x of n minus n. It is equal to 1 minus e power minus j omega multiplied by x of omega. We consider another property, accumulation property. DTFT of sigma minus infinity to n x of k, it becomes equal to pi x of 0 delta of omega plus 1 by 1 minus e power minus j omega x of omega. Convolution property. x1 of n convolution x2 of n. The DTFT of this convolution results in product of two signals x1 of omega with x2 of omega. Next, we consider another property, multiplication. DTFT of product of two sequences x1 of n with x2 of n. It is equal to 1 by 2 pi x1 of omega convolution, circular convolution with x2 of omega. So far we covered important properties of DTFTs. Now we move to certain standard or widely used transform pairs. Before that, we consider a pair of relations called parsevals relations. What are parsevals relations? DTFTs are mainly for non-periodic sequences, or they are meant for energy signals. Energy exists. One can define already defined energy of a non-periodic signal in time domain. Parsevals relations gives expressions for energy in frequency domain. Under Parsevals relations, we need or we are supposed to consider two relations which are mentioned here. First one, sigma n equal to minus infinity to infinity plus infinity x1 of n multiplied by x2 of n. It can be shown equal to 1 by 2 pi integration over 2 pi x1 of omega multiplied by x2 of omega d omega. Here x1 of omega is DTFT of x1 of n, x2 of omega is DTFT of x2 of n. After covering first relation, let us move to second relation. Sigma n equal to minus infinity to plus infinity mod x of n whole square is equal to 1 by 2 pi integral 2 pi mod x of omega whole square d omega. Second one is just it is first one with x1 equal to x2. Left side it is energy in time domain. Right side it is energy in frequency domain. Now we consider some commonly used DTFT pairs. The DTFT, discrete time Fourier transform of delta function. It is called Kronecker delta. We have two impulse functions. In continuous time domain, impulse function is called Dirac delta function, whereas in discrete time domain, it is called Kronecker delta. Its DTFT is 1. DTFT of delta n minus n naught, shifted Kronecker delta. Its DTFT can be found as e power minus j omega n naught. Third pair, DTFT of 1 can be found as 2 pi delta of omega. This is Dirac delta. Fourth one, DTFT of e power j omega naught n can be found as 2 pi delta omega minus omega naught. This is Dirac delta. Fifth one, DTFT of cos omega naught n can be shown as pi times delta omega plus omega naught plus delta of omega minus omega naught. Similarly, DTFT of sin omega naught n can be shown as j pi times delta of omega plus omega naught minus delta of omega minus omega naught. Some more pairs we consider. DTFT of step function can be shown as pi times delta of omega plus 1 by 1 minus e power minus j omega. Next one, DTFT of minus u of minus n minus 1. It can be shown equal to minus pi times delta of omega plus 1 by 1 minus e power minus j omega. DTFT of a power n u of n can be shown as equal to 1 by 1 minus a e power minus j omega. 10th one, DTFT of minus a power n u of minus n minus 1 can be shown as 1 by 1 minus a e power minus j omega. Now we move to transform, which is heavily connected with the DTFT, that is DFT. DFT stands for discrete Fourier transform. It is connected to DTFT. The relation, the definition of DFT is explored in the present slide. The DFT is the appropriate Fourier representation for digital computer realization because it is a discrete and finite length in both time and frequency domains. So this sentence gives the importance and significance of DFT. There is an extremely fast algorithm called FFT, fast Fourier transform, for its computation. The DFT and its sequence are related by, the relations are given here. DFT of a sequence x of n is x of k, which is equal to sigma n equal to 0 to n minus 1 x of n e power minus j omega n. Of course, here omega is 2 pi by n. Now the inverse transform. X of n is equal to 1 by n sigma k equal to 0 to n minus 1 x of k e power minus jk 2 pi by n n. So first is DFT, then is inverse transform. The DTFT of a sequence of finite length n is DTFT. It is x of omega equal to sigma n equal to 0 to n minus 1 x of n e power minus j omega n. Comparing this with the definition of DFT gives, comparing these two, x of k DFT is x of omega with omega equal to k 2 pi by n. So this relation connects DTFT with DFT. Now properties of DFT. Time reversal. DFT of x of minus n mod n is x of minus k mod n. Time shifting. DFT of x of n minus n naught mod n is e power minus jk 2 pi by n n naught x of k. Notice x of n and x of k, these are transform pair. One more thing also we need to keep in mind. DFT of a sequence is also a discrete frequency signal. DTFT is CT signal, but DFT is DT sequence. Conjugation property. DFT of x of n conjugate is x of minus k conjugate. Frequency shifting. DFT of x of n e power j k 2 pi by n, it is omega, n naught is x of k minus k naught mod n. Multiplication. DFT of x1 multiplied by x2. These two are sequences. It is equal to 1 by n x1 of k circular convolution with x2 of k. Circular convolution property. DFT of circular convolution of x1 with x2 is product of x1 of k with x2 of k. Circular convolution and mod, these two are defined here in this slide. x1 of n circular convolution with x2 of n. It means it is equal to, it is by definition, sigma I equal to 0 to n minus 1 x1 of I, x2 of n minus I mod n. M mod n means equal to m plus in for some integer I. Now we come to the end to this session. Before concluding the session, let us recollect the areas, important topics we touched, we covered in this session. Definition, properties, transforms pertaining to DTFT. They are all given. In addition, DFT and its relation with DTFT. This aspect also has been covered. Hope this session is useful to you. We meet again in another session with a new topic soon.